Hello everyone, welcome back. This is 2-3 Celtic Priority Racing Condition and their applications. I'm MU222, and as the title suggests, we will discuss Celtic Priority Racing Condition and how you will apply in actual redstone builds. Now, besides Celtic Priority and Racing Condition, I'm also going to talk about some miscellaneous priority properties to you, such that you can also learn them properly and apply them in actual redstone builds, because they can still be quite useful sometimes. And I'll discuss them between the sections of Celtic Priority and Racing Condition. So without further ado, let's get started on Celtic Priority. Now, before understanding Celtic Priority, we should head on and discuss two definitions first. The first definition is that each redstone component has its assigned scheduled tick priority value if the redstone component uses scheduled ticks. And the lower the value, the higher priority it has to activate or deactivate. So this can be quite a bit counterintuitive at first, because lower priority value doesn't really correspond with higher priority to power. Let's be honest. But then, yeah, you just have to remember this, because this is how the game codes. So lower priority value means higher priority to power. Okay. Now, the second definition is simply about redstone diodes. So there are only two redstone diodes here, which are redstone repeaters and redstone comparators. So these are all the definitions that you need to know. So we can move on and talk about the first property. This is actually already the most complicated one, which is about redstone repeaters. So a redstone repeater has a scheduled tick priority value or tau tick priority value. It doesn't really matter how you call it. Both of them make sense. It has that value of -3 on activation or deactivation if there is a redstone diode facing at the same direction or rotated 90 degrees and is directly in front of it. So basically, you see that this redstone repeater is rotated 90 degrees here, and this repeater is facing the same direction as the back one, and so as the comparator, 190 degrees, one in the same direction. So all of these four repeaters at the back, they will have a scheduled tick priority value, or I would call it in short STP value of -3. So yeah, it only refers to all these repeaters though. So just remember that. Now, notice that I didn't mention this configuration, like two repeaters facing each other, or a repeater and a comparator facing each other. So in that case, that doesn't count. That would count into the next case. So whenever this condition doesn't apply, the repeater would have -1 STP value when turning on and -2 STP value when turning off. So what I mean is that when the initial state is off, it has a -1 value of turning on, and then when it is originally on, it will have a -2 value of turning off. So yeah, that's what it meant. And now we would go on to comparators. This is a bit more simpler. So basically, the essential same condition. We have some redstone diodes directly in front of the comparators, and if they are facing in the same direction or rotated just 90 degrees, then the back comparators here all have an STP value of -1 on activation or deactivation. And when this condition doesn't apply, we would have this case instead, which the STP value of a comparator is just 0. So this also applies when you have two comparators directly facing each other. So yeah. And now for all other components, for redstone components, this only consists of basically redstone torches and observers. They will have STP value of 0 otherwise. And yeah, that's basically all of it. And you might also have noticed that I say components that uses schedule ticks. So what does it exactly mean? So schedule ticks refers to basically components that has some delay when they perform a state change. So for redstone torch, that means turning off and on. Same for observers. But then for other components, they may not be inherently the same. But then as long as they have state changes, they basically have schedule ticks. I will recommend a document for you later if you really want to learn about the actual list of the components that includes all of the components which uses schedule ticks. But yeah, so the main thing to note from this conclusion is that you see Redstone it doesn't have any delay, so it basically doesn't use schedule ticks. This also means that Redstone does not have any STB value. Just notice that. So yeah, now we can head on to the examples. The front ones are the more complicated examples because it shows the specific properties of comparators and redstone torches. The back ones, or the latter ones, would be more about the actual powering priority of repeaters versus comparators versus observers, etc, etc. But yeah, anyways, so let's head on to some examples of comparators first. So a redstone comparator basically cannot turn on from receiving 1-tick pulses from observers, repeaters, or comparators that are directly at the back of it. So you can see here, this piston doesn't fire, same as this. Well, the repeater fires this piston, but the comparator doesn't fire this piston because it doesn't change state at all. And also this comparator. Now you can see this comparator actually receives a 1-tick pulse, but not this comparator. So make sure to notice that. And then the cool thing about comparator is that even though it might not have any state change, like so, a redstone comparator sends redstone updates if it receives inputs regardless of if it can turn on. So say I have this bottom piston. If I flick this lever, guess what? This piston actually extends because this comparator, even though it doesn't really power, it still updates this piston. Crazy. So if I turn it off, see, it turns off. So yeah, pretty cool stuff. So that's a special thing about comparators. And so you have seen from the difference here that this redstone comparator can receive a 1-tick pulse, but not this redstone comparator. So that looks confusing. So when exactly can redstone comparators receive a 1-tick pulse? Now, an example would be it can receive 1-tick pulse if this condition applies. So we have redstone comparator, and then in front of it we have some redstone diodes that are either in the same direction or rotated 90 degrees. So if this condition apply, and the redstone comparator is not powered by a repeater 1-tick pulse, then it can fire. So say if I have these three comparators, so these two comparators can now fire, but not this comparator. And in contrast, if you see here, even though if I place a repeater here, you can see this repeater powers, but not this comparator. The comparator can never receive any inputs from a 1-tick repeater that is giving a 1-tick pulse. So same as here, observers, that still works. Don't worry. So yeah, that's basically the exception, or the case where the comparator can receive 1-tick pulse and emit it. Now, the case for comparator is actually more complicated than a redstone torch. The redstone torch case is actually a bit simpler. So a redstone torch cannot be turned on and or off from receiving 1-tick pulses from observers or redstone repeaters. So we have these here that just does nothing, and in addition, redstone torches can only give redstone updates if it actually turns off or on, unlike comparator's case here. So if I bought this piston, you see nothing really happens because the redstone torch isn't sending any updates. So, yeah. Now, it would be nice if we can have some solutions, some specific solutions to ensure that the comparator can actually, or a redstone torch can actually send a 1-tick pulse. There are a few solutions. So here are some. Basically, all of them uses cauldrons, because, you know, comparison stuff. But anyways, so we have this here, which a cauldron can pull down this comparator. One tick after pushes this piston via the solid block, and then it pushes up out, and then this is a one tick pull, so it will just get split up. And so we can see from here, if I slow it down a bit, you can see this actually one ticks. So is this piston. Like so. So same thing for this one. This one is exactly the same, but just reverse in direction. So you can also replace this with a redstone block actually, and it will also work. So let me fill that up. There you go. And besides these two, we also have this one. So basically, observer to take piston, cauldron, comparator. That also gives a one tick. And redstone block still works. So yeah, very nice. So these are the comparator one tick generators, and it might come in handy if you need them. Now let's generalize more a bit on redstone comparators and torches on the behavior of one tick. So we have a one tick generator here, or one tick redstone comparator generator. So we have this here, so let's just power it, and you can see that this redstone torch actually turns off and on, unlike before. So a redstone torch, we can see from here that it can receive one ticks and also give out one ticks basically from a comparator one tick. So yeah, pretty nice. Now another thing you can see is that if I have a repeater here connecting to another redstone torch, it doesn't do anything. Whereas if I connect it via a comparator and then a redstone torch, it can do stuff. So if you use a conjunction of redstone torches and comparators, and I guess also redstone dust, that can also work because they don't have STP values, so they don't really care. So yeah, as long as you use some conjunction of torches, comparators, and some redstone dust if you wish, then you can have this redstone torch receive a one tick pulse. So yeah, pretty nice. And in addition, of course, you can have redstone torch connecting to another redstone torch, and that also kindly gives you a one tick pulse thingy. So yeah. And in this setup, you can also see if I turn this to a repeater, it doesn't work. So same thing as that one here. Nothing really special. So to generalize, redstone comparators and redstone torches, they're very close buddies, basically. And using them in conjunction, you can always ensure that the one ticks can get through. And when I say one tick, I mean one tick from redstone comparators or redstone torches. So yeah, make sure that you know. And this is basically due to the toxic priority being 0, the value. So yeah, hopefully that makes sense. And that's already the hardest part. We'll come up to some easier ones. So here is a repeater comparator thing. You might recognize this setup a bit, but then in that setup I actually use this as a hopper and this comparator as an observer. But then this is basically the same. So if I press this button, the left piston always powers because this repeater has an STP value of -1. The comparator has an STP value of 0. So -1 means a higher priority to power. So the left piston has a higher priority to power, so it always powers. So no matter where you place it, even if you mirror this, it will always be this piston that powers. Or I should say the piston with the repeater. So yeah. And using this trick, we can also create a 0-tick generator with a repeater powering through the block and then a comparator pushing this piston, fast pushing the block, and then you see if I do this, this is actually 0 ticks. And remember, we have the armor stand test. If the armor stand doesn't even move, this block is getting 0 ticked. So yeah, pretty nice. Next we have this thing here. So how do you determine which piston gets to fire first? Well, we can see these two repeaters are basically identical, but then this repeater has an STP value of -3, this repeater has an STP value of -1, because this repeater has a redstone diode that's facing in the same direction as it, while this one only has a redstone that's in front of it, so -1. So we can see that the left piston powers. Very nice. Now here comes the fun part. We are going to debunk something. If you have watched Dissecting Minecraft episode 15 on Tautics at 5:46, you will see this exact setup here. Now in that video, they basically say that due to Tautic priority, the right piston is going to retract the block instead of the left piston. Now, that isn't the case. If you press this button, yes, the right piston is going to retract the block. We can already see it. But that is actually due to timing differences. Let's slow down a bit. If I press this button, see what happens. The right piston depowers earlier than the left piston, even though they might look like they have the same delay. Well, basically what happens here is that this right circuit actually has 1 game tick less delay than the left circuit when I power it with this button. And this phenomenon is called the input bug, which I will explain more in 2-4 tick counting, input bug, and more on timings. Now, if I properly power this, which would be using a repeater, so basically using a repeater input, you will see that the left piston actually gets to grab the block, not the right piston. We can clearly see this. The redstone repeater has an STP value of -3, and this redstone torch has an STP value of 0. So the left piston always gets to depower, right? So yeah, that makes total sense. So yeah, you can also see from a slow-mo, both pistons depower at the same time. That is the way to avoid the 1 game tick difference between the right circuit and the left circuit by powering through a repeater. So yeah, using a player input would make some circuits inconsistent. So I will tell you more in 2-4 of course. But yeah, the video on basically this setup here, debunked. Very nice. Now we basically have already finished talking about Tautic priorities. Let's move on to some miscellaneous priority properties. The first one being rails and pushing a column of blocks. You have seen this setup before, hopefully, because this is basically from 1-2 properties of redstone components 2 and 2-1 basic locationality and directionality. So the property is pretty simple. When you power a tip of the rail, a straight line rail, powered or activated, it will always be the furthest observer that powers, has the higher priority to power. So you can see this piston powers, and if I flick this piston gets to power. Like so. This is also similar to pushing a column of blocks. The furthest observer always has a higher priority to power. If I push it from here, you can see this powers. Push it from here, this powers instead. So yeah. These examples basically clearly shows the properties. I'll explain why this lever is here later. So yeah, that's basically the rail and the column thing, the priority properties. Now we move on to some actual cool stuff. And this is actually pretty simple. It's just the powering order of observers. So if I flick this lever, you can see the power order of observers, the priority order basically goes as follows: -x plus x, -z plus z, -y plus y. So there you have it. So basically the acronym is X, Z, Y, and then negative first, then plus. Which brings us back to this here. Now, this isn't exactly related to that setup, but from this setup is also the same logic also applies to this. What if we power the middle observer? Well, the thing is, it will always be the negative side observer, the furthest one, that gets updated first. So you can see this is negative Z, this is positive Z. Power this, the back piston powers. Very simple indeed. So that is for you another property. Very miscellaneous. It might not become very useful to you, but who knows, it might be. And then we come on to the next one, which is also about observers. But then this time, it's a bit special because it is in conjunction with pistons. I call this the conductor principle. So here I have these two setups here. You can see in this setup, this piston, the sticky piston is unable to retract the normal piston actually. While in this setup, this sticky piston is able to retract the normal piston because I use a conductor here. And this one, there isn't any conductor, it's just observer directly detecting another observer basically. So yeah, by adding a conductor, you can ensure that this sticky piston would grab the piston always. And if you don't use a conductor, you can always make sure that the sticky piston cannot grab the piston. So yeah, this is a conductor principle. So there you have it. Now we would move on to some examples, such as this one. So this image shows, not this image, this here shows a directional circuit. So if I power this here, you can see both pistons power the top and the middle one, while in this setup, this actually pushes to this middle piston with this line block. Not very nice. We want it to be consistent. How so? We can make use of this XZY property. So if we have here, we have this observer versus this observer. So this observer is facing towards the x-axis, and this observer is facing the y-axis. So this must happen because this observer has a higher priority than this observer. So this piston powers before this piston. Now this isn't the actual direction, because it should be this direction, so we should test on this direction as well. It's the same thing, because this is a Z observer, this is a Y observer. Z always have higher priority than Y, so this piston must power before this piston. Very nice. So that is how we can manipulate some update order thingies or some miscellaneous priority properties to power the piston we want to power first, right at the same tick. So you can see the usefulness of it. Now, that's basically all of the miscellaneous priority properties that I want to discuss. Now I would get on to racing condition. The exact wording of racing condition is very long, so it's better for me to just give you an example. Here we have this observer going to this same tick, and then so one tick, so after this powers, one tick after, all of these observer will power, so they will power including this piston as well. Now if you have learned this properly from this rail example, you would know that if I power from the tip of the rail, this rail always have the higher priority to power. So after this pushes, in theory, you would have this piston that powers, but instead, it isn't. It's actually the back piston, or should I say the front piston here. It's actually the front piston here that gets powered. This phenomenon is called the racing condition. Basically, if these pistons are pushed and they are scheduled to power at this location, then it will always be the front one that gets powered, that has the highest priority to power. Even though we have the rails that would manipulate such that the back should power first, but then due to racing condition, which is more dominant, this actually powers first. And now, if I flick it the second time, guess what happens? Now it will be the back one that powers, because these pistons are not pushed in place. So they are originally in this position already. So the back piston powers by powering priority of activated rails. So this makes sense. The first time I flick the lever, due to racing condition, this piston powers. The second time I flick this, is due to powering priority of rails, so that the back piston will power. So yeah. Now, racing condition has a few situations. This is only one of them. Another one would be that a piston is pulling another piston. And the third one would be not even pulling. It's the front piston that powers and then depowers. And then when you power it at a suitable timing again, the front piston will power again. So these are the three conditions. We can take a look at some actual examples. Here we see two examples that come from, well, 2-1, basic locationality and directionality. These are the exact two examples. We have a folded double extender here. You might think this dust is locational. Well, it is if you just simply power at this place, but then we are powering this here, and then one tick after we power this piston here, and due to racing condition, the front one must power first. So we have this that powers. And then, well, notice, again, this is actually a conductor. It powers this one tick after it powers this one. So, due to the conductor principle, instead of the back one going to push it up like this, it will be this one that pushes, and then this one that pushes. So yeah, conductor principle also applies. Very nice. Here we have this one instead. So this is a double pole, single pole generator. And now, due to racing condition, when this piston retracts, and then because it will power the second time, so this here, it was scheduled such that both of these pistons will fire at the same time, and due to racing condition, the front one is going to power, even though it's quasi-connected. So you can see right here, racing condition also applies. Here we see a new example. This is to demonstrate that the front piston, when the front piston basically powers, it can just power infinitely many times. So we have the back piston that will power, and then the front piston will just power forever. The back piston is just alone. And this is also due to racing condition. So yeah, basically, yeah, if you get the timings correct and tight enough, the front one will always get powered. If you don't get it tight enough, like if I zero tick this, it will actually give a different result. This is not tight enough because I zero ticked it, and the delay is a bit different actually. And this sticky piston will always power instead of this normal piston. So there you go. Hopefully all of these explanations make sense, and yeah. Now I would go on to promote you something, which is a useful list that you can refer to. It is spacewalkers on redstone timings and piston mechanics. So it has especially two things that are important for this chapter. One is the list of components that uses schedule ticks. So I've already linked the documents in my documents, so we can always check that out. And I also put two screenshots there that are especially important for you. So you can always check for the list of the components that uses schedule ticks. And for the STP values, there's also another screenshot of it, which basically summarizes everything I've said in the tile tick priority section. So yeah, there are also some other technical details in the documents, and you can check that out if you're really interested. Although, please do be cautioned, it is quite technical, so read it if you are talented or intelligent, or if you know well enough, basically, on the mechanics. Or otherwise, watching this video is already enough for your knowledge. So anyways, now I'm going to go to talk about the applications of all the priority stuff that we have just discussed, including racing condition. The first one is actually an observerless thing, but then it's also very useful for our learning purposes, because this 4-wide observerless 5x5 bottom setup uses comparators and repeaters in conjunction, and this top redstone dust cross would always have a repeater 1 tick. Well, just always. It isn't actually all the time. We'll have a repeater 1 tick that goes through this redstone dust, and we have already established that the comparators can never receive 1 tick pulses from repeaters, such that basically it doesn't receive a pulse from this repeater. But then we also have this 1 tick comparator generator, so this signal will go through this comparator to power this back dust. So we can basically see how this thing would work. So just imagine we would just shovel blocks inside here, so we need 2 pulses. And then we will also have the bottom that fires. And this will fire at the correct timing in conjunction with this bottom line powering this dust, such that it does something like this. So yeah. And you can see it's not really in sync, because we have this dust here that powers these 2, and then this comparator powers this dust, powers this one. So we also have these here, like so. Very strange. And then for the opening sequence, we would also have a more than 4 tick pulse that powers this repeater, although I will demonstrate it using a 2 tick pulse. And this will actually go through the comparator, but it doesn't really matter here. It doesn't even really retract any blocks. The main thing is that it goes through this 4 tick and then this here, and then it also goes through this bottom circuit here, such that it will also retract this, like so. And then if we give it 1 more pulse, this powers, and then this comparator will just power it again, such that it fully retracts. So we can recap this. Also, this 2 tick is important because blocks will be pushed here, and then this middle dust can power this piston, by the way. So yeah. And then this here will retract this. You don't really have to fully understand how this setup works, because 1, this is a series that's dedicated to 1.11 plus redstone, and 2, the mechanism isn't really exactly the thing I want you to learn. The thing I want you to learn is how this comparator doesn't receive the 1 tick from this 1 tick repeater, but does receive from this comparator instead. So yeah, that's basically what I wanted to show you. So we see a use in observerless doors. Let's see some uses in observer full doors. Here I have this thing. Also, I'm not sure, but then I should place this in the middle. So this is from the top circuit of my 432 block 5x5 seamless full flush cave corner door. So let's just see it working before we do anything of it. We power this with a 14 tick pulse to here. So this isn't the exact input, but then it resembles basically what it should resemble. So I will do this, doesn't really do anything. Come on. The cool thing about this top circuit is that it uses both tile tick priority and racing condition all in one. Again, you don't have to understand how everything works. I'll just show you the important components that makes this thing work. I can't place it. There you go. So due to piston extender layout, we need to have this double extender like this, and can only be powered by this observer. Yay. What happens is that we would have this that powers, this retracts, this goes down, this observer powers this, and then we need to have something to control this such that this piston actually would retract 1 tick later than this piston, such that according to racing condition, this piston will power from the observer here, like so. Or not, because I am stupid and didn't use the correct wiring. So let me just retract this, and then do this, like so. And then we also need to push this piston back. That's basically how this thing needs to work. So let's explain this stuff first. So this manually gets controlled by this piston here with an observer, so that does it already. The second thing is that we have this input here. I used the wrong component. Then hopper. This. 1 tick here. Okay, so this already controls everything, to be honest. Now let's see the total priority that it needs to use. This 1 tick is competing against this observer, because this piston is competing against this piston. According to total priority, this has an STP value of 0. Oh, sorry, -1. This has an STP value of 0. So this piston powers first, like so. So yeah, I'll also just retract these. Now remember that this piston has to retract 1 tick later. We have this observer here, which might seem redundant, but then it's useful in the retraction. During the extension it isn't that useful, but the retraction it is, because this would depower at 1, this would power at 1 and depower at 2, so we have an extra 1 tick. And due to racing condition, as I've explained just now, this piston at this location will power like so. And this piston gets extended because, again, toxic priority. This turns off at 1, this powers at 1, this has an STP value of 0, this has an STP value of -1, so this would retract first, and then this would extend. Now, the thing you need to notice is that you cannot have an unmovable block here. If you have an immovable block here, it actually doesn't do that. Unless you would have, I don't know, I'm not sure if this one works. Yes, this works. You need to have something that updates this, basically. Otherwise, you cannot have any unmovable block here. This is also a very tricky stuff, which is also a reason why I have here a 4-tick repeater. You can't really see it. Let's just use there, a 4-tick, which is movable. So now the triples. The triples are basically just placed here. I'll just use one module though, because the other module works exactly the same. This is the entire triple. Power this. Basically with a long pulse. There you go. That works. Now I'll explain why. I have this here. Now this is a 4-tick, so it will generate 2 pulses. So when this powers, this powers. When this powers, this does powers both this one and quasi powers this one, and this will actually update such that this power, so both of them would extend and retract at the same time, such that this one ticks. The second time this powers, and this one will power. Now, you might think, hey, isn't that locational? Well, if you have the correct timing, it isn't, because due to racing condition, this piston just retracted this piston, and this is after 2 ticks, so this piston will power instead from here. So again, using racing condition, very nice. Another time, this here powers this one. This here powers this one. Well, I should probably just retract the block here, might as well. This retracts this. This retracts this. This doesn't power this. It powers this instead. Because remember from this example we have this just powers forever. So with the correct timing, it actually powers this again. And this finally retracts this. It's just basically that. And that's how basically this circuit works. It's also a very standard circuit. So, yeah, that's basically what I need to show you in this module. It uses both chaotic priority and racing condition in a compact store, that is. So that's quite impressive. Let's move on to another example. This is the 4x4 shutter door by me and Lumendo. It opens in a very fast pace, actually, 0.65 seconds, so we can slow it down. I'm not going to show you the exact timings that it needs to work, but then I will show you some chaotic priority that it uses to make stuff work. We have a few locations actually. We have this one tick repeater going to an observer powering this piston. We also have this lamp going to this observer to this observer. Well, according to chaotic priority, this has an STB value of -1, this has an STB value of 0. So this piston gets to power first. Like so. Now, other things. 2 tick here powers this piston. But we also have this redstone lamp going through 2 observers that powers this dust. Both of them power at the same time. Well, according to chaotic priority, this has an STB value of -1. This has an STB value of 0. This piston gets to power first. Like so, we see here. You might also wonder why this is here, but then it's just for timing. It's basically essentially the same as this one. This observer that needs to extend this longer by 1 tick, such that the timings work. Now finally, there's also this 1 tick here. Observer. These 2 observers power both of these pistons at the same time. Due to chaotic priority, this has an STB value of -1, this has an STB value of 0. You know this piston powers. Very simple. Like so. And that's basically all the chaotic priority that the store uses. The rest of them is mainly some 0 tick generating and just some correct timing circuit such that the store works. So yeah, it's pretty neat though. And also uses some chaotic priorities that you can learn from. Now finally, we would have this piston worm circuit using rails. Yes. If I activate this burnout, it goes wee. Like so. Now, let's explain this. We know that powering the tip of this rail would cause this rail having the highest priority to power, such that this observer, and then such that this piston has the highest priority to power than this piston, so this would push. Let me just grab a lever. And then, because the redstone, the burnout has a 2 tick interval, basically, for every pulse. So this piston gets to power instead of this, because racing condition. This piston just gets extended, so we will retract this. And again, racing condition. This piston will power. Racing condition. This will power. Racing condition just does this. In a lot of racing conditions later, we end up with this position. So yeah, the first time is due to update all the rails or powering priority rails. The second time and a lot of times later is due to racing condition. Yeah. Pretty cool circuit. And that finally concludes all of the stuff that I need to cover in this video. Now I will go to the exercises. Whew. So for this video's exercise, it is quite a bit special again, because not only does it have reset circuits, it also has a lot of short questions, so it requires some wordy answers. Well, not exactly wordy, but then it's just some short word answers that you need to care. So I'll explain few of them that you need to notice. The first one is actually quite interesting. All 4 sub-questions actually come from just a triple piston extender. So it basically tells you what to avoid during the building of a triple piston extender like this. And as always, please refer to the instructions for resetting the circuits here if you need to. And the main focus I want to have is on this here. So we will have this here, and the retraction circuit is basically that you need to build a circuit such that it goes from this position to this position. Very simple. Now, there are a few things to note from this. First is from the question requirement. The bottom dust line must not interfere with the retraction circuit. So this is the bottom dust line. You cannot have anything that the bottom dust line will, for example, get powered here. And you must not have anything that the bottom dust line would interfere and would break the retraction circuit. The second thing you need to notice is that this is a solid block. If you have anything that would power this block, it would interfere with this piston and leaves this block down, and then it would get retracted and it would not match with these blocks. So make sure that either you can retract it back in time or you just don't power this block. The third thing is that when removing these white stained glass, you'll have this power. Don't worry, there's a reset lever here. You just power it back, like so. Now, another thing is, if you need to reset it, I personally suggest you to copy this position here and push these pistons if you need them. It's also written in the instructions below, so don't worry. Now, I'm going to go through 2 more interesting stuff. The first one being this one. This is actually from one of my previous projects, and the experience of it inspires me to make this exercise, because I basically come across with the exact same thing. And also the important thing is that on the right module, after building the circuit here, you need to push this button first, then flick this lever once to check if the condition satisfies. So make sure to do that. Another interesting one is this one. This is actually taken from one of the Redstone requests I have from a Discord user. So you basically need to create a circuit here, and you also need to choose your input device, by the way, such that it matches this position. The pistons doesn't have to be 1 ticked or anything. You can have it constantly extend if you want to. Also in here. Now, the restriction that this have is actually very special. The circuit must also be expandable and with identical circuitry in each layer. So whatever you build here, you must also build the exact same thing 3 times here. And it must be expandable, and all of them just works. So make sure to remember that. That's a fun condition for you. So yeah. I'm not sure if the questions are very hard, or quite simple, because usually a lot of them I give you a very tiny space to work with. So some of you might have some difficulties in it, but don't worry, just try your best and don't feel too bad if you cannot complete it, because there's always the solutions are right behind it, and you can always go through this wall or just tear down this wall basically to view the answers of it if you need it. So yeah, if you need to consolidate your knowledge from this video, please make sure to do your exercises. And as always, yeah, thank you for watching, and I will see you on 2-4 tick counting, input bug, and more on timings. Thank you.